Before further ado, let's get started. Let's get a big hand right now. Let's give them a big hand before we start. Okay, Rafi, on to you. You can introduce and let's get started.
Yeah. Hi everyone. Hope you are doing well.
Yes, we are.
First of all, I would like to thank you. Thank you for taking out time for this presentation. I don't know if you are aware of the fact that for the past 2 months, my team has been working with Sensing Dynamics on machine learning platform. Today we are going to share some insights about the various experimentations, pipelines and process flows run by our team. Today we have Manveer and Simar from my team who have been involved in this project from the very beginning. The presentation would be given by Manveer. And in case you have any questions, Manveer and Arpit would be there to help you out to find the answers. And so now I would like to hand over the thing to Arpit. Over to Arpit.
Thanks, Rafi, for the introduction. I think since we have already lost a lot of time, I'll move on to Manveer. So Manveer, we are on the first slide, so let's get started.
Hello all, I'm Manveer, and I will be speaking about the machine learning pipeline created by Simar and myself, and how it has been used to classify the fruit smells with according to their odor. So is everyone on the first slide right now?
Yes, so we are on the first slide.
Yes, so move on to slide 2, please.
Yeah. Content slide.
So, yeah. This is what we will be covering in the presentation right now: the data description and understanding, the pre-processing and the cleaning of the data, the classification algorithms that have been used by us, the results and evaluation, and then we can move on to the questions and answers.
Okay, we are on
next slide. Next slide, please.
Yeah, data understanding.
Alright, so here I will be speaking about the data, the different characteristics that it has, and how we have used that in our classifier. Are you on the 4th slide, sir?
Yes, we are on data understanding, yes.
Alright, so for the time being, we have worked with 3 analytes. We have received data sets from the Canada team regarding 3 analytes, namely raspberry, tangerine, and grape. Each of these analytes have 200 observations each, and the observations are matrices with 11 columns. So these matrices are the timestamp, the 8 gas sensors of the sensor array, the temperature in the chamber, and the humidity in the chamber. And these data points are stored as CSV file, and the timestamp goes from 0 to 65 seconds. So the experiment is run for roughly 65 seconds. The valid data points, however, in this matrix go only from 2000 to 5000 milliseconds. I'll just explain in a second why that's the case. And there will be a link to a sample data set, so you can open that up, and I can just show what the data set looks like.
Sure. Yeah, we opened the data set, but it's not showing on the screen. We can actually pass on for now. It is opened up on this computer, but it's not showing here. So I'll just show it to folks right here. So this is how the data set looks like. If everybody is able to see, I don't know. It's an Excel sheet with a lot of columns.
Yeah, so I'll just explain.
Yeah.
It's got 11 columns. So there are 11 columns. The first column is the timestamp value. The timestamp goes from 0 to 65 seconds with roughly 100 millisecond step. The remaining 8 columns are the digital values of the sensors, the gas sensors, the digital sensor values that they done. And the other 2 values, the last 2 values, are the temperature in the chamber and the humidity.
Yeah.
Okay, so we can go back to the presentation.
Yes. We are on the graph slide.
So why we're using the data points from 2000 to 5000 milliseconds, the graph here depicts the sensor values according to time. So from 0 to roughly 2000 milliseconds, the system is initializing, and after 5000 milliseconds, the system, the vacuum chamber is being drained. So the sensors actually peak somewhere between 2000 and 5000 milliseconds. So those peak values are what we require for the classification, and those are the ones which we keep for the training purposes. Okay, next slide please.
Yeah.
So how we hope to determine each fruit from its odor is using its unique fingerprint. This fingerprint is what describes the data, and it is what we use to classify the fruits. The 8 sensors respond differently to different analytes, and using that we've been able to classify the fruits. So next slide please.
Yeah. Reprocessing.
So now I'll talk about all the pre-processing tasks that have been performed on the data to firstly prepare it for the classifier algorithm and any sort of pre-processing that might be used to improve the classifier accuracy. So any data modification that is performed pre-classification to improve accuracy. So the next slide please.
Yeah.
Slide number 8.
Yes, we are on that.
So for pre-processing, it mainly includes 3 steps. The transformation, so this is converting the digital sensor values into a change in resistance values, or maybe taking a Fourier transform. I'll just explain in a second why that is. The feature extraction, this is the conversion of the data point, which is a matrix, to a vector, which is what is required by machine learning classifiers. And also at this point, if you want to reduce the number of features in the data set, we might do so by using a principal component analysis. And then we can perform data cleaning on the data by removing all noisy components that is value beyond 5,000 milliseconds, and also any outliers or any noise that may have entered into the data at that point. So the next slide please.
Yeah.
Yeah, so firstly, we transform the data into a change in resistance. What we have is a digital voltage value. We convert that into a change in resistance using these formulas. This has been done in accordance with the Taiwan paper, which demonstrated why change in resistance might be a better metric for the training purposes. It is better accuracy. The first formula explains how the resistance, the sensor resistance can be computed using the resistance of the sensor, which is VRL is the resistance of the sensor at that point. The VRL is calculated using the digital value of the sensor, the one that I showed you in the data point, from the second formula, which is digital value multiplied by 5 divided by 1024. So this returns the value of voltage in volts, and this is further used to determine the change in resistance value, which is done by subtracting the present resistance value from the base resistance and dividing it by the base resistance. The base resistance is calculated from, is basically the resistance averaged from 0 to 2000 milliseconds. So the resistance calculated using the first formula from 0 to 2000 milliseconds with 100 millisecond step is averaged to get the base resistance, and that is used to calculate the change in resistance value. So we calculate the change in resistance value for each point from 2000 to 5000 milliseconds. Okay, next slide please.
Yeah.
Yeah, so once we have once we have decided whether we will use only the digital voltage or the change in resistance, we have to convert the matrix into a single vector. So that can be done by one of the simplest ways of doing that is by averaging or summing the data. So we can simply take the average of all the features present in the matrix, and that reduces the matrix essentially into a single vector. So 200 of those vectors are obtained for each analyte for the training purposes. So this has been computed for both the digital value and the change in resistance value. Okay, next slide please.
Yes.
So converting the matrix into a vector can also be done by taking a row major or a column major conversion. So how this helps is that it avoids the data loss in information. When we are averaging, since we are taking the average of the features, we might be losing out information. So to prevent that, we can just convert the data into row major or column major. So an example is shown here how a row major conversion is done. If we have a matrix as specified A, B, C, D, E, F, the row major conversion is done by simply appending each row after the other to obtain one large vector, and a column major is done in a similar fashion just by appending each column to each other. So this has shown a significant increase in the accuracy of the classifier. Next slide, sir.
Yep.
Yeah, so one more experiment that we ran with the machine learning pipeline was by taking a Fourier transform of the data. Since we are working with time series data, what we tried to do was to use a fast Fourier transform to compute the discrete Fourier transform, and to see if any insight could be gained from analyzing the data in the spectral domain. So we can decide whether or not we use a fast Fourier transform, and it showed like a slight increase in accuracy in some cases. We are transforming the matrix into frequency domain, and it generates a complex number. So the Fourier transform conversion generates a complex number, but we're using the absolute value for the training purposes. Next slide, sir.
Yes. Yeah.
Okay, so if the number of features for the classifier is too large, we can use a principal component analysis to reduce the number of features. So what the PCA does is it combines correlated features into a series of lesser number of uncorrelated variables. So we apply PCA for both the digital values and the change resistance values. And for a normal case of averaging, we were able to reduce the number of columns from 11 to 4. And for maybe a row major conversion where the number of columns increased to 141, we reduced it to 23 by using PCA. Next slide, sir.
Yeah.
So now we can also perform basic data cleaning on the data, which is removing any sorts of outliers from the data, which outliers generally tend to come from noise or some void value which does not have to be considered. We can use a box plot to visualize.
Manvi, we lost you out there. Hello? Can't hear you at all. Internet issues.
So, which part of the measurement? You didn't do the measurement in India, did you?
Yeah.
The sensors?
The sensors have been built here.
Yeah.
The data has been generated here, and the processing of the data is happening here.
So, okay, so you gather the data, send it there,
Yeah.
and do the measurement.
Yes.
Cleaning.
Yeah, we're back. Manvi, you there?
Yeah.
So we were on pre-processing of data cleansing. Yeah, we completed that.
Data cleaning.
Yeah.
On the 14th next slide.
Yes, we are on, completed the 14th slide, I think we talked about, yeah, we are on the 14th slide, yeah.
Alright, so if we in the 15th slide, we are on the 15th slide now, right?
Yeah, 15th slide, yeah.
Yeah. So now I'll be talking about the classification algorithms that we use and the different platforms on which we experimented. Next slide.
Yes, we are on that.
Yeah, so we used two open source libraries for the classification. We used Weka and Azure Machine Learning. We ran supported vector machines, KNN and multi-layer perceptron on Weka, and ran for this neural networks and decision for this on Azure ML. Alright, next slide, please.
Yeah.
So a prerequisite for the classification was splitting the data into training and validation sets. The training set is used to train the model, and the validation set is used to calculate the accuracy of the trained model. We can use a 70-30 randomized split, which is using 70% of the data for training and 30% for the testing or the validation purposes. And we used a tenfold cross validation, which is basically doing the 70-30 split 10 times with different segments of the data to get a better result, to get better metrics for evaluation.
Yeah.
So, next slide, sir.
Yes, we are on that. SPM.
So on Weka, we achieved good accuracy using SVM. We use the LIB SVM library in Weka for classification. We found that to be a better option than SMO from our research and what we could see. all the calculations of the performance metrics were done using tenfold cross-validation, and this was tested with both with and without PCA.
Yeah.
Next slide, sir.
Yes.
So on Azure ML, we were able to see the best accuracy with multi-class neural networks. Multi-class neural networks are good at pattern recognition problems, and under here is a link to a similar problem where wines from different wineries were classified on the basis of taste and color and texture, and there also multi-class neural networks work well. So we've run this multi-class neural networks for our problem on Azure ML. Next slide.
Yes. KNN.
Yeah, so some other algorithms that we used were nearest neighbors, perceptron, and decision forest. So the ones that are stated above were the ones that gave the best accuracy. Next slide.
Yes. Optimization.
So we also worked with optimizing the classifiers. So the screenshot here shows the different parameters on the Vector library that we can modify within SVM to get a better result. The SVM provides their various kernels that on which the model can be built, the linear, polynomial, and the RBF kernel, etc. So one example is that we saw that for using a linear kernel, if we have if for a machine learning task we have a large number of features, a very large number of features, the linear kernel may work better than the RBF kernels when using SVM. And all calculations were done using cross-validation. Next slide, sir.
Yeah. Process flow.
So this is the process flow that we followed throughout this is the entire machine learning pipeline process flow. First, we work with the data conversion and cleaning, that is converting it into the change in resistance values, or using only the voltage value and removing any noise. The transformation, whether or not we would like to take a Fourier transform to analyze it in the spectral domain or to analyze it in the time domain. Then we move on to the feature extraction and reduction. This is the conversion of the matrix to a vector or the reduction of features using PCA. Then we go on to the cleaning, which is removing outliers and extreme values from the data, any noise from the data that may still be remain. And then we go to the classification and evaluation on the
Yeah.
next slide.
Yeah.
So now I'll be speaking about the results.
Yeah.
Are you on slide 24, sir?
Yes. Yes.
The accuracy of any machine learning classifier is analyzed through the confusion matrix. The confusion matrix will list the two positives, the two negatives, the false positives, and the false negatives in the data. The true positives are the correctly identified conditions, correct positive cases identified as positives, and two negatives are the false negatives identified as negatives. So these are the correct cases. And similarly, false positives are any wrong cases in which the condition was identified as positive but it was actually negative. And false negative is the opposite of that. So the metric for evaluation can be the accuracy, which is the true positives plus true negatives divided by the total number of test cases. Or other metrics include the precision, which is stated as the sum of true positives divided by the sum of test outcome positives, and the recall, which is the sum of true positives divided by the sum of condition positives. So another metric for evaluation is the X-score, which is a sort of weighted average of the precision and recall. Okay, next slide. So for our purposes, we've measured the accuracy, the precision, the recall, and the F-score. We have not considered specificity because our case is not a binary classification; it is a multi-class classification. So true negatives are not clearly stated. So that's why we left out specificity. And the link provided here can show you the report that we generated for all the machine learning pipelines. So sir, can you open that?
Oh, we can skip that for right now, and we are not able to show that. So just move on to the next slide.
All right. So I'll just explain it for a minute. If anyone wants to see it, you can just go there. It shows the different combinations of the machine learning pipeline that we've used. the different combinations of the pre-processing task, the machine learning algorithm that we use, and the results for each and every algorithm. So there are filters there and everything, so you can analyze which.
Let me try to see if I can show that on the screen also. Hold on a second.
Arpit, I think you have not downloaded that report. That is also there in the folder, Sensing Dynamics folder.
No, I think the report is still there. I'm just trying to share it on the screen. Let's see, and you will go from
Okay.
Yeah, I think you can escape out of the presentation and just drag it over.
Yeah.
Skip.
I'll show this.
What is this?
Yeah, powerful.
Escape from the presentation.
Yeah, we are seeing that right. Yeah. Go ahead.
Is it open, sir?
Yeah, it is open. Go ahead.
Yeah, so I'll just as I said, the first column shows which platform on which we ran the classifier. The second set of columns is the pre-processing tasks which were conducted. The first states whether or not we use the voltage or the change in resistance value. The second specifies whether we used for principal component analysis for reduction or not. The next slide shows the feature extraction technique that we use. This can range from the average reduction, the row major conversion, or the column major conversion. The transformation, which specifies whether or not we used an FFT or whether or not we analyze the data in the spectral domain. Then we move on to the classification algorithm, which states the algorithm which was used. And the results show the accuracy, the precision, the recall, and the F value. Also, if you can use the drop-down menu of the accuracy, you can see the pipeline which gave like 100% accuracy, the best accuracy.
Yeah, hold on a second. I'll do that.
It's right there.
So I think there are roughly.
Yeah, I'll just open it up. Yeah, about 100%.
So
Yes.
So there are 8 pipelines, like we ran 46 such combinations. So there are 8 pipelines which are giving 100% accuracy. If you see the first row, we can see. Sorry, if you see the feature extraction column, you can see when using an SVM, a row major and a column major conversion works well because it gives us 100% accuracy. And for neural networks, similarly, average reduction and row major or column major conversion can show 100% accuracy. Some of the other algorithms are shown in the last 3 rows. The second to last row shows an SVM classification using a linear kernel. So that showed a better accuracy, and also an SMO classification using a complexity factor of 9 that also showed 100% accuracy. So these are the rest can also be viewed as in required. Alright, so we can go back to the presentation then.
Yeah. Hold on a second.
Yes, so slide 26.
Okay, just one minute. 26 slide. Okay. Challenges, right?
Yeah. So you can move on to the next slide.
Yes.
I'll be speaking about some challenges that we faced with the existing data. So we have to be careful about what we mean by achieving 100% accuracy, because the number of data points that we have and the observations are quite limited. We are working with like 200 observations for each group, and also the reduction of the data set from matrix to a single point. It greatly reduces the number of data points we have for classification, for training the algorithm. So we have to be careful about that. There is a slight inconsistency in the timestamp. The 100% 100 milliseconds time step is not constant, and that might create some problems. Then also the we should always hope to create more data, the amount and the variability, increase the amount and the variability of data to help us to come up with more robust and better models. All right, next slide.
Yeah. Working with
Yeah, so recently we've been provided new data sets by the Canada team. So they actually they improved on some of the problems that are listed. Next slide, sir.
Yes, we are on that.
On 29.
Yeah, 29.
So they actually added volume information, that is the volume of the analyte used in the chamber, and also the speed at which the pump was operating. So this basically increases the variability in the data, and also the greater amount of data has been sent to us, so we can use that to create new models and to test our existing models for weaknesses. And but the number of features in the model is still the same. There are 11 features from timestamp to humidity. Right. Next slide. Yeah, so we'll be testing the new pipelines with different combinations of volume and pump speed. We'll be building new models with new test sets, and also we'll be using our old models. We'll be testing the accuracy of our own models on the new sets, and the model generation and prediction we will be doing on the new data set alone, and also on the combined data sets to come up with better models. All right.
Yeah.
So next slide. So these are the references that we selected in the presentation, and now we can move on to the questions.
Yeah. So they are done. So if there are any questions, so please feel. Yeah.
On the PCA and also feature, let's say feature compression and feature reduction, and denominator reduction and feature selection, like the data that's been used for selection of the conversion matrices, and also the selection of the features were done on the whole data set, or on only training data set, or in an inner loop cross validation?
So
I'm sorry, the voice is breaking up a little bit. So could you just explain?
So I think the question
again?
Yeah. So the question that was asked was that did we use only the training data set for any kind of feature reduction that we did,
or part of it? Or like, for instance, an inner loop cross validation, or just a training data?
Yeah. So was the training data set only used, or any other different kind of techniques to do the order reduction, feature reduction?
So the reduction was done on the training data set.
Okay.
The feature reduction you're talking about converting it into converting the matrix into a vector, or the principal component analysis for reducing the features.
Yes, I think that
that's the answer.
That's the answer, yeah.
And the other question, right? When you were adding volume, like that was about 2 million sample points.
Yeah.
Now you have 100% accuracy. What is the point? Are you making actually involving more classes, more parameters, like varying contextual information, or what is the reason for that?
Yeah, so the question, Manveer, is that right now we showed on the slide that we are changing the volume, and we already received 100% accuracy. So what do we expect to achieve with the new data set where we are having different kind of volumes? So can you answer that?
Yes, the volumes and data set, we want to see if that changing the environmental factors can have any sort of effect on the accuracy of the data, or accuracy of the model, I'm sorry. So earlier we were not working with specified, we were only working with one volume of the analyte. So now increasing the volume, we are hoping to increase the variability in the data set and come up with a more robust model. So we want to see that whether or not the volume will have any sort of change in the data, in the accuracy of the classifier.
Would you also increase the number of classes, or not just also, let's say, types of sensors, these things as well? Like not type of the sensor, but maybe different manufactured sensor.
So the question is, he's asking, do we also think of increasing the type of different sensors that we will be using to test it?
And the number of classes?
And the number of classes, does it also change the number of classes that we are going to predict?
So yeah, if we are currently using 8 sensors, and some of these sensors are actually testing for the same substance within the odor. So we're using an average of these sub-sensor values, like for the ones which are picking up the similar substance. By increasing the number of sensors, we can basically generate a more complex fingerprint for each analyte. And the more complex the fingerprint, like the more features that we note of each analyte, the more analytes we'll be able to differentiate among. So the answer to that would be yes. If we increase the number of sensors,
yes. Are you there, Manvi? I think again. Yeah, is there any other question I can answer? Not a problem.
Yeah, I have two actually.
Yeah.
So I'm curious what the variability was in accuracy. Like what was the low end?
Low end. So with the Manvi, you there? Yeah. So there is a question from Matt. Matt is asking what was the level of variability we saw in the accuracy of whatever tests that you have done so far. How much, like, what variation did we see in the accuracy? Like, what was the lower bound? Upper bound, we know about 100%. What was the lower bound? Like, what was the least accuracy that we saw?
yeah. So we were okay. I'll just bring up the
Excel sheet?
the report slide again.
Yeah. Okay.
Yeah, here.
I'll just bring that up. Yeah.
We were working with different combinations of algorithms to see which algorithm gives the best accuracy. So of course we did not go out of our way to get a poorer accuracy. So if some sort of classifier was giving a low accuracy, that would be nearly 70% or 60%, we did not include it in the report. These are all the pipelines that give like an 80% accuracy at least and above. So for the algorithm stated, we can vary the pre-processing steps and maybe change the accuracy a little bit. It might go up or down a little bit, but it will remain within like a 10%, maybe a 5% interval of the current accuracy. So if you pick any pipeline, like any particular row from this report, and change for that particular algorithm, change the pre-processing steps, there might be a 5 or 10% increase or decrease in the accuracy. But otherwise, we try to combine only the ones that give the best possible accuracy. So any algorithm that we use that was not giving 80% accuracy, we not include in the
Thank you, Matthew. Thank you, Manvi. Matt has another question.
Yeah. So second question is using Azure and
Weka.
Was there any way to get a sense and quantify the processing requirements and the memory requirements associated with each of those methods? I'm just thinking, how can we tie this back to infrastructure costs? Right?
Yeah. So I think the question that Matt is asking is that while we were conducting these experiments, both on Azure ML and Weka, do we have a sense of what kind of performance requirements are required? Performance with respect to memory, the CPU, power, and the storage. So do you have sense of that, Manvi? Like any thoughts about that?
Yes, sir. So I can state for a fact that building an SVM classifier takes a little bit of time. On a standard laptop, it took about a few minutes of time to create the model and perform the cross validation. There are different logs which are generated each time an algorithm is run, so those can be analyzed to give a particular memory requirement. I cannot give details right now, but there are definitely methods of doing that. And any sort of algorithm which is run on Azure ML is done on Azure virtual machines as it is. So over there also there are many logs that are generated which we can analyze to see what the memory requirements are like.
Right.
Yes, some algorithms are definitely more memory intensive than others. The pre-processing part is basically just code written by us which can work on any laptop. The algorithm itself, every algorithm has a different requirement.
Right. Okay. Fair enough. Any other questions? Yeah, go ahead.
I have a couple of things. Can you go to the slide number 3?
Yeah.
But number 3 before presenting the results.
Number 3.
Yeah, I saw number 3 here,
Oh, okay.
but it was actually like 20 something.
20 something.
Just before the slide that has the results, you have here.
This one?
Process flow. Yes, the 22.
22. Okay. So when we are on the slide number 22, the process flow, there is a question regarding that. We'll see. Yeah, go ahead.
Here,
Yes.
I don't understand why you are doing FFT here.
Uh-huh.
If at the end you're taking the magnitude of the number.
Yes.
Well, you have real numbers, and you are doing FFT or the FFT, and then you have absolute value gain. So why do you need the FFT?
So I think the question here is that in the process flow we showed a transformation where we have used fast Fourier transform. The question is, since fast Fourier transform produces imaginary numbers, but for our classification purposes we have only choose the absolute numbers. So what's the need of a fast Fourier transform here?
Yeah, so the fast Fourier transform was an experiment that we ran just to see whether or not it can give a better accuracy. This is not a compulsory step in the process flow. This can be omitted, and for some of the pipelines that give the best accuracy, we've seen that fast Fourier transform did not work very well. What we thought was that since we are working with the time series, analyzing it in the frequency domain, in the spectral domain, might give a better accuracy, may provide some sort of information that can be used for the classification. That's what we were hoping to find for the Fourier transform when using the Fourier transform convention. So for some pipelines, it showed a minor increase, and but the others, and I think there's one pipeline which shows 100% accuracy that used Fourier transform. But this is an optional step, and this is only done to see and to analyze the data in the spectral domain. So to see if any sort of information can be added when analyzing it in the spectral
So
domain.
maybe we have another question. Yeah, go ahead.
Yeah, no, it's on the same question because you're transforming into frequency domain. Of course, you have a new space, but there is no extra information.
Well, in fact,
In fact, if you're taking the magnitude, it's the same information. You don't need to do that.
So that is what
this is real.
Yeah.
This is real. It's based now. There is no high frequency, so this is a real number. The resistance is a real number, fully real number, and you're going here to the transformation you have phase now.
Yeah.
It's meaningless because it's hard. The spectrum is hard. You don't need it. Then you go here.
I think that's for future extraction purposes. They want to like read the information is there, but just to make the information more linear for the.
no, the question is, which information are we interested in? Is it from the raw signal or not? If you are from the raw signal,
It should be
you should
a-
apply the FFT
Yeah.
on the raw signal, right? From the digital points, not from the delta R over R.
Oh.
Because you want to go from temporal domain into the frequency domain. You extract the frequency components using an FFT. You do that on the raw signal, namely the signal you collect directly from the eNose, not from the delta R over R. You're already reducing your signal to basically 1 point, from 1,000 points or 4,000 points, whatever, to 1 point. And thereafter you apply the FFT. It's like extracting almost no information. There is no information there to
But
extract.
that is incorrect. Actually, that is incorrect. Actually, this is not 1 point. Actually, what it does is that for all the voltage values that are in the matrix, it just converts that into resistance. So it is actually still a matrix. You only
No,
get 1 point
one signal.
only at this point of time.
No.
This is still matrix.
What about the response from one signal?
No, yes.
Yeah.
So if your response is for testing and
Yeah.
to try a different thing, that's fine.
Yeah.
But from my point of view, there is no.
No, it is not question of point of view. It is a pipeline. You can pick and choose whichever you want. Actually, they have proved that there is a pipeline by choosing this. There was 100% accuracy. So, I mean, we can debate in theory, but practical shows something else, and that is why we have used these things. And the reason was very simple, actually.
I will
Yeah.
pass. Sorry,
Yeah.
I will pass also do this, but I will pass the time series as well.
Actually, time series is being passed here. Actually, that is why we are doing.
Okay.
Yeah. So this is
So it's not only information from the after the.
No. So this is time series data. This whole pipeline. So just for explanation purposes, we are actually working with the time series which is 65 seconds. It's not like a very historical time series. It's only 65 seconds. However, in those 65 seconds, we generate almost 1,000 kind of values because every few milliseconds we generate a value. So you, like, there was a graph I'll just show where we show there was a graph that goes back to that. Yeah. So if you see this one, right? So basically, this is a time series actually. This is time information, okay? And these are the various values, actually the values. And these are each of them is different sensor actually. So actually this is a time series you see. So in fact, we also tried, there was dynamic time warping. And so there is another technique, dynamic time warping, just specifically for time series analysis, but we didn't see much better results for it. Even in using fast Fourier transform, we saw one pipeline, which I'll show again, which still gave 100% actually accuracy. Other pipelines were not. So essentially, even at this point of time, this is actually a matrix because we are getting values for each of them and for all these different time series. So it is not one point. So I just wanted to correct that.
The FT was applied to the entire system.
Yes, absolutely, absolutely. To entire
So that makes sense.
Yeah,
that makes sense.
That is what it was.
That makes sense.
Yeah, that's right. But now the info you have after this is all frequency domain. So you lose all the memory of the system.
Yeah.
If you don't pass this to the next step,
Yes.
you have no memory at all. That's really important for the next.
Yes.
That's block.
So basically,
If you keep the
how is the
frequency
memory?
domain, it's memoryless. You don't have history now.
Yes.
And if everything you're doing is with after the FFT, you have no memory at all. So you're missing all that information.
However, some part of the memory
Missing the
is
time series.
basically we are not. So the data set that we have, it is actually persistent data set. So basically we have a CSV file that persists till the data. So even if we needed, let's say, I'll go back to the process flow, right? The pipeline. Let me just open this is the actual, the pipeline is this. Actually, if you see, each of the row that you see is actually the pipeline. And it tells which are some of the things that have been used in the pipeline. So for instance, when you say here FFT has been used, this has not been used. So each step, we persist the data. And nowhere we are losing the data actually.
Yeah, something. Look at this. This is telling you didn't apply here.
But yeah, but I can show you with the application of this also, there is a pipeline which showed 100%. Let me just show you that.
But why, if in the time of play you have 100%, why do you apply the FFT?
The problem is the data that we are working with is very small. So even when you say 100%, when we see, so we case generated actually additional data set, and we changed the volumes of different data points. The case is working on that, and when we generated the different data sets, actually some of these classifiers that are bit that are showing 100% are actually dropped in the accuracy. And the reason for that is the initial data set that we used was very, very minuscule. Now that case has produced the new data set, we are seeing that the existing algorithm no longer working well. That is why we have to change.
That was actually my question, because in the pipeline, there was a slide you were talking about tuning the parameters of the classifiers, the methods, and here you are reporting the best result, right?
Yeah, here are the best.
With the best, and that could be, in the machine learning term, they call it double dipping, because you are fine tuning and maybe only by chance you are ending up to a set of parameters that give you best accuracy. However, if I was reporting like a distribution of the accuracy, so which one was most likely capturing the information. Yes. So it could be just this is a double dipped method or or
Yes, so I think that's a very good question. There is a chance. Actually, we know most of these cases where we are getting more than 90% is actually overfitting. The challenge we had was initially data set that we had was like few hundred data points that Manbir already mentioned. So now when we have generated more thousands of data points, we are passing them again through the same model, and we are already seeing that the accuracy is actually dripping. It's not coming.
However, you could maybe separate. I know yes, you have a very limited number of samples, of course.
We have more.
Exactly. Like in this case,
yes.
Some researchers, what they do, they separate some data totally unseen as a third step, of course. Or, for instance, some of these parameter tuning are in inner loop cross validation tuned. Then that will definitely increase the reliability of the performance.
So right now, what our team is working on is actually, so Case has produced some more data for us, and he's producing further, and he's automating that as well.
Yeah.
Meanwhile, what our team is doing is that, so this is the first set of models that we have already built. The pipeline is already there. Whenever Case produces new data, right, That data now goes through the same classifier and try to compare whether these results are not there. Then next step after that, which they showed future actions, is that we will merge the two data sets together, and then we'll build another model and see what the results are there.
So that volume helps you to also tune the parameters in inner loop cross validation on other approaches.
Absolutely.
True.
So that,
Yeah, sorry.
yeah, go ahead.
No, I assume you're splitting the data, right?
Yes.
Like
Training
training and
set and
testing,
testing
that
set.
you will never see, right, for prospective testing.
Absolutely.
Otherwise, you will always have 100%.
Yeah, so because in the starting itself there was 70-30% split as was explained in the presentation. So the point is, the more data we get, we have to reach a stage whereby no matter how much new data you bring, we get somewhere above 90% accuracy, then we can say our classifier is robust. As of now, this is more like an experiment, right?
Sure.
We don't know, like, these are like...
The pilot study.
It is actually the experimentation has been done with several of them. Our intention is that our vision is this, that we should move on to a stage whereby this process can be also automated. We can just click a button, build me 1,000 models, give me the best results from that.
But if you have that data, you have to apply deep learning. I mean, forget about all these.
Yeah. So for deep learning, first let us come to a stage where we have that, like petabytes of data, then we'll apply deep learning to that. Yes. So yeah, you had a question?
No. The other thing is, I'm trying because we have a very good hardware. So, the hardware is really diverse. So
yes.
all these sensors has tons of different spaces. And I think it's if you work a little bit more on the feature extraction before applying FFFT, before you do any averaging, because averaging is a bad word here.
Yeah,
Each time you average is a bad
word.
Because you're killing all the information that the hardware is giving to you.
Yes. So essentially, to that point, actually, the averaging is just one of the techniques. We show that it is not good technique, and that is why you see we do row measure conversion and column measure conversion. So what row measure and column measure does, it includes each and every feature. There is no reduction that happens. It converts all. So we have a matrix. It converts all the matrix into a one column itself.
It's a scramble.
Yeah, it's a scramble. So actually, when we did that, you see some of those places when we did that, we still did not get 100%. Whereas with the average reduction, we still got 100% in some cases. The reason for that is the bias. It is actually biased data. So data is very, very small.
Yeah.
So there is a lot of bias in this data. So don't see it as like gospel truth, right? It is not. It is just fact-based analysis that this is a small data set that we have. These are the results that you see with that small data set. Our intention is, our hope is, now the next data set that we'll get, we'll first try with those algorithms that gave us like 100% results. If they do not conform with that, then we start seeing. So it has given us like a blueprint. What to try? Well, there are so many things we can do, right? If I just, see the number of like options that we have here, right? We can easily get into like thousands of pipelines just by keep changing the parameters. So we're trying to optimize like how we can get to the best result. Do you have a question?
I'm thinking, did you reflect about the ab initio processes that are involved here? So I have the feeling that you are trying to do multiple data treatment on the data without knowing what you're looking for really in the beginning.
So basically, what we are looking for is very simple. So if I go back to show you an example. So what we are looking for is this. So I think 1 year and all probably you guys can drop. I know it's pretty late for you guys. I think I'll end it from here. Okay, thank you very much, guys. Raki and Marvi, you can drop off. Thank you very much. Thank you guys.
Thank you, sir.
Yeah, thank you.
Thank you. Have a great day. Bye.
Bye.
Have a good one. Bye.
So basically, you see, this is what we are actually. This is we can keep doing it. So basically, this is what we want. Okay. So essentially, the data set that we get is